Hi guys, so welcome back, and this is the last of the little videos on entropy for this week. Next week I'll put the rest of the videos up, which will cover the rest of the pack, but this is as far as I want you to get to at the end of this week. So in the last two videos we looked at the entropy of the system, and we said that was to do with the chemicals and were the chemicals becoming more ordered or more disordered. In other words, were they losing entropy or were they gaining entropy? And in the previous video, we looked at the entropy of the surroundings, basically what was happening to everything around the chemicals. So what was happening to the solution, what was happening to the air, and so on. And again, we were looking at whether or not they were gaining or losing in entropy. But those two things on their own don't tell us that the reaction is going to work, that the reaction is going to be spontaneous. It's only when we put the two things together that we can work out whether or not the reaction is going to be spontaneous. So it is that total entropy change, not the individual parts, the total entropy change, which tells us whether or not the reaction is going to be feasible or not. And that's what we're going to look at in this last video. So you're going to need your notes, a pen, and surprise, surprise, a calculator again. So when you've got those things in your notes, we're on page 13. Okay, so you should be at the top of page 13, and we're talking here about the second law of thermodynamics. In other words, we're saying that for a reaction to be spontaneous, in other words, one that works, goes without us having to constantly push it or add, raise the temperature or do something to it, but any reaction that is spontaneous, the delta S total must increase. Okay, now that total is made up of those two parts that we talked about earlier on. It's made up of that system, that's our chemicals, and our surroundings. So when we combine these two values together, we get our delta S total. So either of one of these two could be negative, but as long as the other one is a bigger positive, as long as this number here, this total, comes out as positive, we say that the reaction is feasible. In other words, it will go. So we're going to have a look at an example of this on this page. So we want to calculate the total entropy change for the following reaction. We're asked to calculate basically delta S total, and we're given some information to do that. Okay, so delta S surroundings. If you remember the little formula, it's minus delta H over T. Okay, and I'm just going to put those numbers in. So I'm being given the value up here for my reaction. So it's minus, brackets again, minus 65. I'm not going to forget that I've got to change that into joules. So I'm going to remember to times by 1,000. And I'm going to divide that number by 298 Kelvin, because that's the temperature at which I'm doing the reaction. So that should come out as plus 212.8. Sorry, write my numbers down. Plus 218.2, and that is in joules per mole per Kelvin. Okay, well, I've written all the numbers down correctly. Notice I've included a sign, and I've included my units. I'm not worrying at this stage about significant figures. I'm writing quite down a lot of them, because I won't deal with sig figs until I get to the final answer. Okay, so now I want to work out my system. So delta S system is equal to the products where I end up, take away where I started. Okay, so I've got 1 of 83.4, take away one of these and one of these, so minus 39.7 and 69.9. And again, if I plug that into my calculator, I should get minus 26.2 joules per mole per Kelvin. Now that makes sense because I'm going from 2 moles of reactants to only 1 mole of product, so that's a decrease in entropy, and also I've got a liquid here which is turning into a solid here, so I'm expecting this number to be negative. Okay, but as I said before, it's not the individual numbers that matter, it's when I combine the two. So we're going to now work out my delta S total. So we're just going to move down the page a little bit. There we go. So delta S total is basically those two numbers added together. So it's 218.2 take away 26 0.2. So I get positive 191.92. And I'm going to write that out as plus 192 joules per mole per Kelvin. And that's my final answer. Okay, so it doesn't matter that I've got here a negative system. It doesn't matter that the chemicals are becoming more ordered, because that's more than offset by the increase in the entropy of the surroundings. In other words, the surroundings are getting so much hotter at this temperature that this is quite a big increase, especially compared to the small decrease I've got here. So overall, I've got a positive number. So is this reaction feasible? Yes. Why? Because my delta S total is positive. And it's as simple as that. Any reaction is feasible only because the delta S total is going to be positive. If it's negative, then we say the reaction is not feasible, what we call not spontaneous. Okay? So turn over to the next page. And we're going to do the same, but this time we're going to do it at 2 different temperatures. We're going to try the same reaction, or different reaction, sorry, but we're going to do it at 2 different temperatures. So what I'd like you to do now is pause the video and have a go at doing this reaction, first of all at 400 Kelvin and later on at 1000 Kelvin. And I hope you've had a go at those A and B on that page. So I'm just going to go through them in a little bit more detail. So at 400K, we're going to work out our delta S system. And that's going to be 2 lots of my carbon monoxide. So that's 2 lots of 197.6. Take away a carbon, which is 5.7. And carbon dioxide, which is 213.6. Okay, and if I plug this into my calculator, I get plus 175.9, again, joules per mole per Kelvin. Now, I need to ask myself, does that make sense? Well, it does in this case because I've got a positive value here, and that makes sense from my equation at the top of the page, because I'm going from a solid and 1 mole of gas to 2 moles of gas. So I'm expecting to see a positive delta S system. But this reaction, you'll notice, is endothermic, plus 173. So if I work out my delta S surroundings at 400 degrees Kelvin, so remember I've got to do this at 400, it's 173 times 1000 divided by 400 Kelvin. Now, because this is endothermic, the whole thing is going to come out as negative, because if you remember, delta S surroundings is equal to minus delta H over T. Okay, so again, if I put that into my calculator, I get minus, because this will be a negative number, 432.5 joules per mole per Kelvin. So at 400K, delta S total equals 175.9 minus 432.5, and that comes out to minus 257 to 3 sig figs. I've just given my answer there, 3 sig figs, joules per mole per Kelvin. So this is not feasible. Why? Because this is a negative number. So this entropy change here, this entropy change of the surroundings, because it's such an endothermic reaction, is bigger than the increase in entropy we get from the system. So again, when I combine those two, I get an overall negative number. Now I'm going to do exactly the same thing, but I'm going to do it at 1000 degrees Kelvin. Now I'm going to assume that my delta S system does not change. So I'm going to make the assumption that that value stays as 175.9. Sometimes it's not particularly valid, but in this case it's pretty good because they're already gases, and carbon has a much higher melting point than that. So I'm quite happy with that as an assumption. And that's joules per mole per Kelvin again. The value that is going to change definitely is my delta S surroundings, and that is minus delta H over T. So again, I've got minus 173 times by 1,000, but this time it's also divided by 1,000. So my answer is minus 173 joules per mole per Kelvin. Now, at 1,000 degrees Kelvin, my delta S total is equal to 175.9 take away 173. So now I get a positive number, positive 2.9 joules per mole per Kelvin. Because in this case, this entropy term of the surroundings, the energy we're sort of putting or taking out of the surroundings, is offset by the increase in entropy of the system. Okay, and the reason for that is it's done at 1,000 degrees. Now, if you remember, I said back in one of the previous videos that at higher and higher temperatures, this term becomes less and less important because it becomes a smaller numerical number, either positive or negative. So it starts to affect the total less and less, and the system starts to dominate. And because our system is positive here, as we get higher and higher temperatures, that starts to dominate. This becomes less important, and because this is positive, we get an overall positive value. So as we increase the temperature, the reaction becomes feasible. And this is why endothermic reactions in specifics generally work better at higher temperatures, because the surroundings term for an endothermic reaction will always be negative. So you need this number to be as small as possible for it to work. So you want a really high temperature. So most endothermic reactions you have to heat in order to get them to work. You've got to get them to a high enough temperature. Likewise, an exothermic reaction actually works better at lower temperatures. It actually is more feasible. We will talk about yield later on, but it has a better yield at lower temperatures. Okay, which leads me on to the last bit for today. We want to work out exactly what temperature this reaction does become feasible. So we know that delta S total has to be a positive value. So we can kind of sort of cheat slightly and say, okay, well, the smallest value I can get is 0. Because I know if I nudge it a little bit above that, it'll become positive. So if you like, the temperature at which delta S total is 0, that's my tipping point. That's my point at which the reaction becomes feasible. So I'm going to sort of basically set my delta S total to be 0, and I'm going to work out what temperature would that become true. Now, I'm just going to go through how we do this in a little bit more detail. There's sort of a long way and a short way. So this is a long way, first of all. We take our delta S total, and we say that is equal to the delta S, the system, plus delta S surroundings, and we know that that equals 0. We know that our delta S system, and I'm just going to swap in here my term for the surroundings, which is minus delta H over T equals 0. So delta S system is equal to delta H over T. Notice, because I brought it over to this side, I've lost the negative sign. Therefore, T is equal to delta H divided by delta S system. Now, you can either go through the algebra, or you can basically just learn that. You need to know that value there. Okay? So, the temperature at which delta S total is 0, the tipping point, can be worked out through this little formula. So I'm just going to put that formula in there. Now I need to be very, very careful that I make sure I've got things in the right units. It doesn't matter if they're in kilojoules or joules, but I can't mix and match. So I can't have one in kilojoules and one in joules. Okay? So my delta H, I'm going to turn that one into kilojoules. So I've got 173 times by 1,000, and that's going to be divided by my system, which is 175.9. Okay, and when I put that into my calculator, I get 984 Kelvin. So basically I can say that is the temperature at which the reaction becomes feasible. End of this week's entropy videos. So we've looked at the basics of entropy, we've looked at entropy of the system and the surroundings, and in this video we put them together to make the total, and we worked out the tipping point, in other words when the reaction went from being non-feasible to feasible. Okay. Please keep working on this. Make sure you're doing all the work. You can also check out our carbonyl videos as well, where we went through the whole of the rest of the carbonyl pack. And remember, that needs to be uploaded by Friday. Okay. Next week, I'm going to be uploading videos on the last half of the entropy pack and also the first part of the mass spec IR and chromatography packs. So they'll be coming up very soon in the early part of next week. If there's anything that you want me to go over, either via email or if you want me to do another little video on any aspect of the entropy or the carbonyls notes that you don't think we covered in enough detail, please just drop me an email. You all know my email address, or you can use the Microsoft Teams to send me a message. Keep working, stay safe, stay home, and I'll look forward to speaking with you soon. Take care. Bye-bye.